So we're fortunate today to have Shang-Ping from Scripps, who's going to talk about a paper that came out led by Qihua Peng on surface warming induced global acceleration of upper ocean currents. So for the winds and currents webinar, this is really speaking directly to the currents aspect of what we're looking at. And I'll let you take it away, Shang-Ping.
Yeah, thank you, Sarah, for the opportunity to speak at this webinar. So basically, this is mostly a modeling study, as you might have thought. It's to kind of ask the question, how does the ocean circulation might change in a warming climate? So the paper is mostly based on the work done by Qihua Peng, who is a postdoc at Scripps at the current time, and published in Science Advances earlier this year. Okay, so this is a model simulation in response to 4 times carbon dioxide concentrations in the atmosphere. So taking the radiated forcing of the increased carbon dioxide concentrations in the atmosphere. And as you can see, the most robust change is the global warming, kind of every part of the ocean and land basically is warming up at magnitude about 4 to 5 degrees Celsius. And then there is a change in the surface salinity distribution, a decrease in the Western equatorial Pacific, and decrease over subpolar North Atlantic, and an increase in the rest in the rest of the North Atlantic. And a little maybe surprise to some of you in the audience is the wind change in response to CO2 increase is rather incoherent. You see it like they tend to be small scales, and also especially among models, they are highly variable among models. So I would, we have basically, I'm showing the 3 surface changes because they are traditionally taken as surface forcing from the atmosphere. So basically the SST change, surface salinity change, and surface wind change represent 3 distinct forcings to the ocean. And then in terms of wind forcing, basically, over most of the world ocean, the wind changes are incoherent and very highly model dependent, except in the Southern Ocean. So in the Southern Ocean, we see across models, the westerly wind intensify and shift to the south, closer to the South Pole. So this kind of also kind of introduces the method we're going to use. In other words, we're going to use an ocean GCM, and in this case, MIT GCM, and adding delta SST, delta sea surface salinity, and delta wind one at a time, and see what happens. So what happens basically is the sea surface warming. It basically dominates the upper ocean circulation change, not the winds, delta winds, not the salinity. And I guess salinity, you might have thought it's probably going to be minor, except in the subpolar North Atlantic. But the major result is the surface warming is the dominant forcing for wind-driven circulations of the upper ocean. So let me briefly explain why that's the case. So this is a kind of a box model of stormal solution and Western boundary current. So the subtropical gyre is known to be driven by the wind curls between the subtropical traits and mid-latitude westerlies. So what the subtropical circulation is going to respond to a surface warming? So this is two model experiments we did, one by imposing a delta SST only, and one by imposing delta wind forcing only. So you can, and the shading is the upper ocean dynamic high. So you just see that in response to surface warming, this coherent surface intensification of the subtropical gyre. Whereas in response to wind change, much of the subtropical ocean, the current change is rather incoherent and not, and except in the equatorial ocean. So in the equatorial Pacific, actually the wind change, the equatorial oceans are highly sensitive to wind changes. Therefore, equatorial ocean is the exception to what I'm about to present. In other words, the wind changes are important in the equatorial ocean. So at least for the subtropical gyre, the surface warming seems to be a dominant forcing. So we are going to kind of consider that scenario change further. So basically, what happens is without wind change, because in this experiment we keep the wind stress constant, not to change. So the wind, without wind change, one needs to conserve vertically integrated mass transport constrained by the sewage transport as written here. So when you add CO2 in the atmosphere, it's going to warm up the ocean like this. And then the surface warming, because the warming is going to be confined above a certain isopycnos, right? The thermocline, the ventilated thermocline, or maybe even unventilated. So it's going to be confined above the thermocline, and then the warming will cause the sea level to rise like this, and that's going to intensify the mass transport by the subtropical gyre. So that is not allowed because the wind has not been changed. So that requires you to lift the moving subtropical gyre to a shallower depth, so that the mass transport v times h can remain constant, dictated by the sewage dynamics. So that, in other words, the net change is we're going to see an intensified surface circulation, but the mass transport requirement will cause the lower moving layer to decelerate. Basically, the moving layer is going to become shallower to conserve sewage transport. So that is exactly what we see in the ocean model when we impose a uniform surface warming. So the subtropical gyre accelerate at surface, but decelerate or maybe getting shallower in the lower layer. So that is a barrel. In other words, this is a kind of a baroclinic change, right? Upper level acceleration, lower level deceleration. So that is the response to surface warming. And then that's the case for the subtropical gyre of North Pacific. And then when we impose the surface warming and we look around the world ocean, and basically you see like even in the North Atlantic, the subtropical gyre accelerates at the surface, but it will change if we introduce the surface salinity, as I'm going to present a little bit later. And then another kind of a strong acceleration happens in the Southern Ocean, in the Antarctic circumpolar current, ACC. You just see this kind of a robust acceleration across the Southern Ocean. And this change is robust across all the CMIP models as well. So yeah, so basically when we impose surface warming, the global surface circulation accelerate. I forgot that the percentage is something like 50-some% of the ocean. So the red arrows indicate the change is in the direction of the current mean the direction of the mean current at this in present climate, and blue is deceleration of the prevailing current. So you just see it's the arrows are mostly red. Yeah. Okay. So that is yeah. I guess in a sense a lot of world ocean belongs to subtropical gyre. That's not terribly surprising, but the ACC acceleration is a bit surprising. So I just briefly explain why the Southern Ocean we now expect ACC to accelerate. So this is kind of basically the meridional overturning circulation of the world ocean. So the deep water forms in the subpolar North Atlantic, and upwells in the Southern Ocean in the wind-induced upwelling region, and then the eddies try to in the Southern Ocean. There are a lot of mesoscale eddies in the ocean. So the eddies try to kind of reduce the slope of the outcropping isopycnos. So that the white lines represent the mean isopycnos in current climate, and this is zonal mean transect of latitude in the Southern Ocean and the depths of top 1,500 meters. So the white is mean isopycnos. So you can see basically the sloping isopycnos indicate there's a sloping upwelling out of Southern Ocean from the deep overturning circulation. So the upwelled water was last in contact with atmosphere hundreds, if not 1,000 years ago. So it basically very effective absorb anthropogenic heat of the warming atmosphere. So the whole ocean heat uptake is tremendous in this upwelling region, but that ocean heat content change, right? So this red shading represents the ocean temperature change. So the ocean temperature change, ocean kind of the upward waters absorbs the anthropogenic heat, and is being advected northward by the Ekman flow in response to the westerly wind. So in other words, the ocean heat content change is going to be displaced north of the ocean heat uptake peak here, right? So this displacement is due to advection by the ocean currents, especially the Ekman flow. So that is kind of the warming pattern we expect to see in the Southern Ocean. And then, as you might have thought, in the southern flank, on the southern flank of this strong warming in the Southern Ocean, the geostrophic current indicates acceleration of the ACC. In other words, a change in the direction of the ACC. So that is basically the model simulated the zonal current change. So that is in the model. So we kind of now expect, because the sloped upwelling in the Southern Ocean, we expect to see an accelerated Antarctic circumpolar current. And that has been actually observed from the Argo observation. So from Argo, we see basically the top 2,000 meter ocean in the Southern Ocean is warming up, and not surprisingly, on the poleward flank of this ocean warming, we see this in the second panel. We see this red shaded area that indicates the zonal current change is positive in the direction of the mean ACC, and the line contours are the mean ACC zonally averaged simulated. Although this is not simulated, this is really observed from Argo, and we use a visual surface satellite altimetry to derive surface geostrophic current. and using Argo observed temperature to calculate the geostrophic shear. So you just see the acceleration is pretty deep and certainly deeper than 2,000 meters. The Argo can measure. Anyway, so at least this Southern Ocean ACC acceleration has been confirmed, validated in Argo and satellite altimetry observations. And of course, the surface wind acceleration has been observed in various data sets. And then, yeah, so I'm not going to skip this part. But I just briefly kind of present something we call ocean surface heat uptake. So because the ocean, it takes the ocean mixed layer about a decade to be in equilibrium to the radiative forcing change in the atmosphere. But it takes much longer, hundreds, thousands years for the ocean to reach such new equilibrium. So in the meantime, the ocean is far away from equilibrium. So the ocean basically absorbs the anthropogenic heat to slow down the surface warming that would otherwise taking place. So the ocean heat uptake in the CO2 forced climate change scenario is mostly concentrated in the Southern Ocean, as I have explained. You know, upwelling, the wind-driven upwelling allows very effective uptake of anthropogenic heat. And another place is in the subpolar North Atlantic. So as you zonally integrated ocean heat uptake, you see the Southern Ocean stands out, and in the Northern Hemisphere, basically this peak in the Northern Hemisphere is due to the slowdown of Atlantic meridional overturning circulation. Yeah, so what happens is in the North Atlantic, the surface salinity decreases a lot, and that together with the surface warming reduces the surface density, and the water in the winter mixture is no longer dense enough to sink all the way to the bottom. So it would result in a deceleration of the Atlantic meridional overturning circulation and its western boundary current. So that is what most models simulate. So the deceleration of AMOC, of course, reduces the poleward transport of heat, and therefore allows the ocean to in an anomalous sense take up the anthropogenic heat. So that is basically what ocean does. So in the ocean heat uptake is confined in the subpolar ocean, and in Northern Hemisphere confined to North Atlantic. Okay, so that I have very quickly kind of gone through the possible changing upper ocean current simulated by models, admittedly, in response to carbon dioxide increase. So in response to sea surface warming at delta sea surface temperature forcing, we see the arrows are mostly red, indicating a global acceleration of the ocean surface current, including the ACC and the subtropical gyres of the Pacific and in the Southern Ocean basins, in the Southern Hemisphere basins. And then when we introduce the sea surface salinity change especially to the subpolar North Atlantic, we see a deceleration. The blue arrows are starting to appear on the western boundary of the Atlantic basin across the equatorial western boundary, anomalous western boundary current. So that's due to the deceleration of AMOC. And the last bit I briefly introduced was the equatorial oceans remain highly sensitive to wind changes, and therefore wind changes are going to be the dominant driver for the equatorial oceans. And unfortunately, the current observations are highly ambiguous and in some sense contradicting what the models are projecting. So models are projecting a weakened trade winds and intensified warming toward the Eastern Equatorial Pacific. But the observations so far have not shown evidence that that's the warmer ocean we are going to see in the future. But of course, the observations include a lot of internal variability and long-term decadal modes of variability. So it's a mess. So that may be I think one of the strong rationale, for reliable climate record of the wind and the currents, and that's what I'm going to imply. So I guess Sarah said, we would like to kind of brainstorm how the important physical processes for climate change can be studied with the new satellite mission. Yeah, so I think that's an important thing to do. And just from the modeling perspective, so I guess the exercise I just presented kind of suggest maybe the models could be up to the job to quantify the three-dimensional ocean current change, ocean temperature change, density change, using good models and of course reliable climate records of sea surface temperature, salinity, and wind. And those all three variables are currently observed by satellite missions. So here, even from the model perspective, even models can be useful diagnostic tool. We still need a surface forcing and of course in ocean observations to see how model does and how everything is changing. Anyway, I think I'm just going to be going to stop here and join the discussion.
Thank you, Shang-Ping. This was great. Questions? I see there's a applause of hearing. So if you have questions, you can put them in the chat, raise your hand. And I see that Tony Lee has his hand up.
Thanks, Sarah. Hi, Shang-Ping. Thank you very much for the very nice seminar. I have a question, clarification rather. You said that the wind changes are not expected of the typical projected changes predicted by climate model, which is the weakening of the water circulation. Is it correct?
In the equatorial Pacific,
Right.
Yeah, the models project, most of the models are projecting El Nino-like warming pattern with
Right.
a slowed water circulation.
But in this case, you don't see that, or?
Oh, that in the equatorial oceans, including Pacific, the wind changes are still important driving force for ocean circulation change. So with water circulation slow down, we expect to see the surface South Equatorial current to slow down as well. Yeah, in models. Mm-hmm. Yeah.
Mm-hmm. Right. So this is the nominal 1 degree model, correct?
Yeah, but I guess that there are, NCAR and at least the NCAR has produced 1/10 degree ocean simulation in response to carbon dioxide increase, and atmosphere is something like 1/4 degree or something. Yeah. So they began. I think that there began to be some high resolution eddy permitting, eddy resolving models of the ocean began to appear.
Right. So I was going to ask if you or your colleagues have looked at what happened in the maritime continent and the exchange between the Pacific and the Indian Ocean in
Oh,
response to all these
I
questions?
think Andy is here, so they have published paper, and many other people also have looked into the model simulation. So the models are projecting a slowdown of through flow. The total transport from the Pacific into Indian Ocean.
Thank you.
Thank you.
Thanks. Andy, you want to go ahead?
Hi, Shang-Ping. Thanks for a nice seminar. Just to clarify, these were not coupled simulations, right?
No, these are the MIT Ocean GCM, with prescribed surface forcing. But
Okay.
we did compare with the original CESM couple simulation, and they're reasonably similar.
Then okay, so then I guess then a follow-up question, if you have thought a little bit about the coupled experiments, would be you are seeing this intensification. I guess I'm mostly paying attention to the Southern Ocean because I've thought about that a little bit more. You're seeing that over sort of 1 to 2 decade timescale. Do you think that it will persist, or are there processes that would respond to this ocean heat uptake in the northern part of the ACC that may, over time, allow the ACC to sort of revert back to its sort of similar zonal transport that it had before?
Yeah, that seems to be the case. Although we haven't looked into this issue specifically. But what Andy is saying is basically there's a fast ocean response, takes about a decade or two, but there's a very slow ocean response that will take decades, centuries, and longer. And that people call slow ocean response. So the slow ocean response, judging from the sea surface temperature and the surface flux change, is kind of opposing in other words, it's gradually reducing this Southern Ocean uptake, and therefore I suspect the warming gradient also probably reduces. So that over time, it seems the ACC acceleration might be slowed down by itself. Just it seems to be the case. Although I haven't checked the current system itself.
Yeah, I think I will just point out. I think it is important to do experiments and coupled models because it's not only the sort of interior processes that are changing the slopes, but it's also the surface, density distribution that's sort of constraining what the large scale ACC tilt looks like. So
yeah, certainly, because the time scales of ocean, distinct time scales of ocean response. Yeah, good suggestion.
Claudia.
Hi, thanks a lot. It was really nice. I was wondering whether in your explanation of the intensification of the subtropical gyre in the Pacific as a response to the warming, you basically came with this constraint from this Sverdrup balance and the fact that the winds are unchanged, and therefore you need to have this surface intensification. I wonder whether this qualitative argument can be turned into a quantitative one, and so if you can come up with an order of magnitude estimate of the predicted change in the Sverdrup flow, and whether that matches what you actually observe.
Yeah, so that turns out to be, I guess, in the 1-layer model, maybe 2-layer model, it's rather straightforward. But kind of quantify this I guess we did try some ventilated thermocline model and so on. Yeah, I guess this is definitely a good suggestion, and we have made some initial attempts, but since maybe in terms of formulation or calculation, it's not as straightforward as we thought. Yeah, but if you have a specific suggestion as to the formulation and how to calculate that, we would love to work with you. Yeah.
I was thinking that it might be interesting and nice, but I don't have a straightforward.
Yeah, but you
way
usually
of
have
doing
a,
that, of
yeah,
course.
yeah. It just seemed to be more complicated. Yeah. But you know, the mechanism seems to be rather straightforward, but I guess qualitatively.
Thanks a lot.
I'll ask a question. Trying to think about satellite missions. Satellites are proposed to last 3 years. If we're lucky, they last longer. And that's clearly not enough time to look at the sort of century scale processes that you're looking at here. And so that leads to questions about how we connect what we can observe with what we can understand from models. One thing that observations can give is a baseline. We can say we're going to get great observations for the duration of the satellite mission, and that's clearly valuable. But the other thing that we can try and do is look at processes. And I'm wondering if any of the processes you're looking at would show up in a seasonal cycle, for example.
Yeah, I saw a little bit, you know, because that's the mandate. Yeah. So that is, at this point, at least, not that straightforward, except that what I can see is it seems that the world ocean so far seem to have 4 different dynamic response regimes. And one of them, the equatorial oceans, seem to be highly sensitive to wind changes. So there remains a very strong coupling between surface wind and surface and equatorial currents. So that may be a lesson, you know, at least qualitatively, I learned from this calculation. In terms of more specific processes, so I feel maybe that, you know, in general, the increased stratification, you know, all what I've been presenting here seem to have to do with the stratification and vertical shear. So in that general, in that sense, I think there's still a lot, you know, just given the surface warming is going to be, the stratification change is going to be a leading cause of ocean surface current. So understanding, studying the stratification effect on the wind shear, especially because the wind current missions are going to measure, you know, the top centimeter ocean current. So that may be another kind of a reason we need to study, you know, how the shears might respond to wind and other forcings. Yeah, it's too general, maybe.
Tony.
Yeah, Shang-Ping, another question. Coming back to the topics of changes in the tropical Pacific, I recall that the freshening pattern is in the Western tropical Pacific, right?
Yeah.
So that presumably is related to enhanced precipitation and the shift of perhaps the convection center of water circulation. And so if you have that pattern of salinity changes together with a equatorial current, which is towards the east, right? So that might shift warm pool edge. So this is a force model results, right?
Yeah.
But in the couple context, regular question raised by Andy about couple versus force simulation, the outcome might evolve in time, right? So once this pattern depict the initial response, but then it may evolve in a couple contexts is what I'm trying to say in a equatorial Pacific.
Yeah, so salinity, yeah, definitely, because it's basically if you allow time, the salinity is probably going to change. Yeah, so yeah, I guess the salinity pattern in the tropical Pacific is more complicated than the surface rainfall change. Surface rainfall change is actually is the rainfall actually increases in the east as well, but
Mhm.
more maybe
Right.
increase more in the east. So I
Right.
think this has to do with the E minus. Not only has to do with E minus P, but also upwelling, back,
Mhm.
the summer kind water and so on. So I think circulation is probably very important in this part. It's
Mhm.
definitely more than the precip.
Right. Yeah, that's a good point. And in fact, you see the symmetry of changes across either side of the maritime continent.
Yeah.
I would have expected a more continuous pattern in terms of the blue, but it's not.
Yeah.
That itself is interesting.
Yeah.
On the Pacific side, there might be couple feedback is what I was trying to say to this freshening pattern and change in the tropical circulation.
Yeah, it's of course E minus P is a factor, but it may not even be the dominant factor here.
Mhm. Yeah, thank you.
Any other questions?
Shang-Ping, sorry, this is Roger. Could you just clarify again whether these are related to the equilibrium responses of the models or if this is transient?
The model we ran for the ocean, we first take this couple CO2 experiment in the transient adjustment stage, and then take the change in the surface density, surface salinity, SST, and put it in the ocean. And of course, we need to integrate the ocean for a while. So I think it's about 50 to 100 years maybe here. So I think we are here to capture so-called the fast ocean response, more or less, or the transient stage of the coupled adjustments to CO2 radiated forcing. Certainly not equilibrium.
Okay, great. Thank you.
I guess I'm still trying to understand if I can ask one more question. You presented the subtropical gyre acceleration as something that really depends on a sphere
Yeah.
transport, but that's shallowing the upper layer. And so does that actually make the upper ocean more responsive to the wind? Does that have an additional acceleration effect because you've shallowed that upper layer?
Yeah, so it's more sheared in the vertical. Yeah, so it's basically, yeah, so that is an example of how the stratification could cause shear, but not in the kind of a traditional kind of Ekman or turbulence sense, but this is basically invasive theory. So yeah, so that is due to the conservation of transport. Yeah, so yeah, I guess that one would argue it's already in the ventilated some kind or even multi-layer models previously. So I guess in that sense, yeah. I guess one point I thought I wanted to clarify is the conclusion here. There's a big caveat here for wind change effect. Just because we have taken the multi-model ensemble mean of the CIMIP and use that to drive the ocean models, right? But let's say we have 20 different CIMIP couple models, and each of them simulate different wind patterns of wind change. When you average them up together, the wind change kind of basically disappear. But in individual, that doesn't, our results do not kind of rule out the possibility in individual models and even in the reality, the wind changes could be larger than presented by the multi-model ensemble average. So this is a big caveat. And in fact, in different models, the wind curve changes are much larger than the ensemble mean for sure, just because uncertainties among models. So that is that's another kind of a maybe put the equatorial ocean response to equatorial ocean current change even more sensitive to the wind change forcing. So that is something I wanted to see, but yeah, at least I got an opportunity to clarify.
Well, thank you. Are there any other questions? If not, we'll wrap up.
Sorry, if I may ask one more question.
Yeah, go ahead.
Because this is very interesting. So on decadal and multi-decadal time scale, would it be possible that there could be a surface warming pattern that might, spatial pattern that might resemble the this centennial warming pattern that you're trying to assimilate? And if that's the case, would one be able to pick that kind of epochal period and look at a response subtropical gyre to see whether you got this surface acceleration and subsurface deceleration?
I think it's highly unlikely the internal natural variability of the Earth's climate system, of the ocean atmosphere system, will have a centennial warming pattern, uniform warming pattern.
Even regionally?
No, because that requires additional energy. Because uniform warming of the ocean will emit more infrared radiation into space, and that would violate the planetary energy balance. So the pattern has consequences. So ENSO, for example, is warm, causes El Nino causes warming in the tropics, but basically leaves the rest of the planet alone in terms of zonal mean as surface temperature and so on. So therefore is associated with a very small energy perturbation, whereas uniform warming has a strong consequence to planetary energy balance. So that I don't think that's allowed to vary that much.
Okay, thank you.
Well, if that's the end of the questions, then thank you very much, Shang-Ping, for a really great talk.
Thank everyone. Yeah, have a good day.
Big round of applause, and we really appreciate you joining us.
Thank you.
Stop
Thank
the
you, Shang-Ping.
recording.
See you.